This is part 4, talking about The Beginning of Infinity by David Deutsch. We're continuing in chapter 1, but this time we're not going to make any progress in the book. I'm just going to go off on the side and talk about induction more, because I think people could use more help with it. It's a tough topic, and I talked with David about it a lot, and I want to share some of my knowledge. If you just read David's and Popper's books, you're not going to find out everything that they knew. There's a lot more that didn't fit in the books. So there are a lot of ways to approach induction, and today I'm going to do 2 that I think are pretty simple and easy, but useful. I want people to get a more concrete idea of what it means, rather than abstract theory. So we're going to look at some pictures. The pictures represent observations. It's not a perfect representation. When we look at things with our eyes, it's a bit different than one frame from a camera, but it's close enough. You get the idea. So, are these similar or are they different? Do we have a repetition? Have we made 2 similar observations or not? What's the pattern? You don't know. You can't answer. There's no way to answer. It depends what our goal is, what we're looking for. There are many ways that these are similar, and there are many ways that they're different. And there's no way for you to say how similar or how different they are without some sort of standard of measurement or comparison. There's no default automatic standard that tells you whether these are similar or different. So I wanted people to be able to understand, with an example, how 2 things can be similar in many ways and different in many ways. So we're going to go through some of the similarities, and then some of the differences. And I could have made much longer lists. You can try it yourself. Like, if you come up with 10 things that aren't on my list, that could be a useful exercise, a way to practice. So similarities, they both have trees, they're both photos, they're landscapes, there's no people, there's no supermarkets. And you can imagine how I could make this list infinitely long by listing things that are not in the photos. There are no planets, like whole planets in the photos. There's tiny little pieces of a planet, but no whole ones. I think. I mean, maybe somewhere in the sky right there is a planet that got no pixels in this photo that represent it. Maybe one of the pixels is a slightly different color due to a planet, though. That seems possible. That's an example of how it's hard to know what you're looking at. Observations are not as clear-cut as people sometimes seem to think. They both have some mist in them. The mist looks pretty different. Like this mist right here versus this like fog and the clouds. But it's mist in both cases. It's water vapor, right? So it's the same thing in some sense. Both of them have brown, and you could come up with more detailed versions of that. Like, you could come up with specific ranges of wavelengths of light and say that both have that. And you could do that for many, many different ones. And you could use decimal points and end up with infinitely many different ones. It could be like the wavelength is 3.01 to 7, or 3.001 to 7, or 3.0001 to 7. These are not the real numbers for light wavelengths, but hopefully you got the point. That you could actually do this infinitely many times, and then you have infinitely many different similarities because both of them have light in that range that you just specified. So there's infinitely different many ways to compare. Not necessarily useful, but they're there. And the issue of what's useful is a tricky issue. It's not something that induction just specifies in a universal way. It's something that we get from our theories, from our ideas, from our explanations. And so if you need to know which of these are useful in order to do induction, and you need to have your theories and your explanations in order to know what's useful, then you would have a circularity problem with induction if induction was supposed to be how we got our theories and explanations. Because you need induction to get the explanations, you need the explanations to analyze the observations, and then you need to analyze the observations to do induction, so you're going in a circle. And where do you start? You have a chicken and egg problem, so it doesn't work. Okay, so some differences. Visible sun in one of them, but not the other. One has more orange than blue. They have different amounts of ground, different amounts of sky. One has birds, the other doesn't. Different time of day, different viewing angle to the trees. One of them might be from a helicopter or something, although it might not. Maybe there's just a hill there. The trees have different masses and sizes and count. Like, there's a different number of trees in each photo. And you could come up with many other characteristics of trees, maybe different species. And you could do things like, does the photo feature a tree that is more than 1 kilogram? What about 1.1 kilograms? What about 1.11 kilograms? You could go on and on and on, and you get infinitely many ways to compare things. Tree trunk angles is another one. So all of the trees have slightly different angles for their trunks relative to the ground. So it brings up the issue, like which differences and which similarities matter. You can't just say look for similarities or compare and see how similar they are and how different they are. You have to know which similarities are important and which to look for. Inductivists might say, well, that's only 2 data points. It's only 2 observations. So let's look at more. Does this help? Does repetition help? Does more data help? It's kind of chaotic. Here's 17 different photos. Is that better? Is that useful? Now do you know what the pattern is? Now do you know what's similar and what's different across your data set? And which of the similarities and differences are important? The data doesn't tell you. You could probably come up with something reasonable, but it wouldn't be deriving it from the photos. You could divide these photos up into groups in many different ways, depending on what your project is. Like, you could have a project where color is important, so you have the photos divided up into categories based on what is the most dominant or striking color. So like this one would go in the red pile, and a bunch of these would go in a green or brown pile, but this one would be in the white pile. And this one here is kind of yellow. That's one way to divide them up and say which ones are the same, e.g. Have a lot of green, and which ones are different, having a lot of red rather than green. But you could do it in many other ways. You could divide it up by like fewer trees or many trees. You could divide it up by how many people are in the photo. You could have a data set with thousands of photos, and a lot of them have people or man-made buildings or stuff like that. So these all end up in the same category. They're all like nature photos rather than civilization photos. And actually, it's tricky. How do you divide up these photos? How do you know that there are 17 different photos here? What you see is one image. It's one large image on your screen, right? There's no labeling. There aren't outlines around the images. I just put them up against each other. So the way you know where one starts and where one ends is you have an idea of what is a normal scene on Earth. But it's not inherent in the data. So one way to look at it is you can tell that there are 17 photos and where they start and end. But could you rigorously explain that? Could you turn it into math? Could you formalize it? Do you know exactly how it works? Do you know exactly what's happening in your brain when you do that? I don't think you do. None of us know that. Our science is not that advanced. Our philosophy is not that advanced. It's not all figured out to that level of detail. So if you don't know exactly how your thinking is working in detail, maybe that's a reason not to assume it's induction, to be open to other possibilities. To think maybe you don't know and maybe other alternatives are worth looking into. Now, you might also complain about the data. Maybe the data is not good enough. Maybe that's the problem. So here is more data. Instead of a bunch of like completely different looking photos, and they're not completely different, they have similarities like trees, but you have some intuitive sense that these photos are all pretty different, whereas these 4 are very similar in a lot of senses, although not all senses. You can find differences. You might not even notice the differences right away, but they are all different. So if you look at this, is this useful? Like, my goal is to give you sort of an intuitive sense. Is this level of repetition of 4 very similar pictures useful? Have you learned something? Does this tell you what to look for or what's important or what matters? is getting a bunch of similar data a good approach that's going to help you understand the world? Well, these were merely similar, but different. What about some that are the same? What about repeated observation? Here are 4 identical photos. Is this helpful? It's not helpful, right? So hopefully that gives you a little bit of an intuitive, concrete sense of some of induction's ideas not being as practical and useful as they might sound when you actually look at it. When you look at this, and it's right in front of you. Does it look useful? Is it actually helping you with something? So I have another example for a way to look at induction that's completely different. No more photos. So which sequence of numbers looks more like a pattern to you? Which one do you think you understand better? Which is less ambiguous? We've got 1, 2, 3, 4. And we've got 1, 2, 3, 22. And these also relate to data and observations. Any observation can be written down as a number, or a sequence of numbers for multiple observations. There are ways to make numbers equivalent to your data, or whatever you observed. Like a photo can be written down as one large number. Okay, so everyone thinks the first one is simpler, it's more obvious, you know what number comes next, you're more confident about it, right? Whereas with the second one, you're like, I don't know what's next, it's hard to tell, right? That is your intuition, and that's a completely reasonable intuition, but there are a couple issues here. So the first one is each sequence could be continued in infinitely many ways. So they're both infinitely ambiguous. This is a kind of technical, abstract point. Maybe I'll go into it more next time. But that is not my point here. I'm not trying to rules lawyer you with some kind of technicality. I don't think it's really a technicality, but never mind. We'll set that aside. So let's change the scenario, not just in the abstract, what number comes next. But let's look at known patterns today that our society cares about, numbers that actually mean something to people, sequences that people have cared about, written down, thought about, stuff like that. Right, so we're limiting it. We're ignoring the infinity of patterns no one cares about. Now, is the first one better? Are you confident? So there's this thing called the Online Encyclopedia of Integer Sequences. And you can type in sequences and it will look for them and see what sequences fit the numbers you type in. So I typed in the sequence 1, 2, 3, 4. And it displayed some results, and it said that it found 11,441 results. By the way, they have 342,531 sequences in their database right now. So they have a lot of sequences, but it's very, very far from all sequences. They're not just entering random arbitrary sequences. These are ones that they've gathered and curated as meaningful to human beings and mathematicians and scientists and so on. These have all come up in some way. Someone has cared about them. Okay, so 1, 2, 3, 4 is actually highly ambiguous. Just from this limited data set, there are 11,441 sequences it could be. There are many different continuations. Not as many, because there's more than one that's going to continue with 6 as the next number. But there are still hundreds, maybe thousands of different numbers that could be next. So it's highly ambiguous. It's hard to tell in our society, in our culture, what sequence that is. What about 1, 2, 3, 22? Well, this one, when you search it in the encyclopedia, there are only 19 results, so it's much less ambiguous. There are only a small number of sequences, it might be, that our society has ever cared about. So the weird-looking one, this may be unintuitive to you, but it's actually much less ambiguous. It's much more clear. You have a much better pattern there, because it fits far fewer sequences from the set of all sequences our society is interested in. If you just look at the set of all possible sequences, limited only by like logic or physics or something, then they're just infinitely ambiguous. But so we narrow it down to what our civilization knows about, and this one is much less ambiguous. If it was a math test and they said what number comes next, and you got this one, you would have like a 1 in 19 chance of getting the right answer if you could use the internet and look it up, or you knew this offhand somehow. So your odds aren't so bad, but with this one, your chance of guessing the right one, just knowing that it's a sequence that our society knows something about, your chance of guessing next is very poor. You probably have under a 1% chance of getting it right on your math test. So the point here is patterns are not quite what people assume they are. There's a different way to look at them. Here's another one I looked up. This is 10 ones in a row. I thought that the repetition and the similarity would be interesting. That's related to induction, right? So in this case, there are 2,799 different sequences that have 10 ones in a row in them. So the next number could be another 1, but it could also be a lot of other things. In this sequence, the next number is a 2. So one objection you might have is that we should look at the start of the sequences rather than anywhere in the sequence, and that'll narrow it down a bit more. I wanted to address that because there's a few notable points about it. First, people often disagree about where a sequence starts. For example, if we're counting, should we start at 1 or should we start at 0? Also, many sequences can be extended infinitely to the left as well as the right. So, for example, with counting, well, there's -1, there's -2, there's -3. You could start anywhere. So if you have a sequence that goes from -infinity to +infinity, in terms of how many numbers there are, as potential inputs, like indexes to the sequence, then there's no obvious starting point. You just have to start somewhere in the middle. And when we observe nature, we don't start at the start. We're coming in the middle. Nature was going on for a long time before humans existed and started observing anything. So actual observations, we come in the middle. The only time we can observe something from the start is when we define what the something is. Like we're doing an experiment and we just define the start and the end point. And then we can observe from the start. But the laws of nature don't really work that way. And our observations of natural reality are not like that. We can categorize things and we've decided what is an event and where it starts and ends. But nature, it's just this ongoing process, and we're somewhere in the middle. That's all there really is. The order we bring to it, in terms of start and end points, is our thinking and our interpretation, except possibly the Big Bang or something like that. But any kind of science experiment we do, or anything with our observations, we're not observing any natural starts or ends that nature may have. So induction intuitively feels like it works because you pay attention to only a few patterns. Out of all the many, many patterns, only a few come to your attention. You don't find random patterns. But how do you do that? Induction doesn't tell you which patterns to find and why those. It doesn't give appropriate guidance for that. Historically, it's based on naive ideas, like you clear your mind of bias, and then you let the uncorrupted truth flow into you through your senses. And that you try to be a passive observer, because when you think you're changing things and causing error, they've thought that we are a source of error. Our thoughts can be wrong. We can be deluded or incorrect. So if you just stop thinking, that's how you can get to the truth. That is not a good approach, though. It's only by thinking and interpreting that we can understand anything, but that idea clashes with the historical meaning of induction and the tradition. People have tried to change it and rescue it, but it started in a bad place. So the reason you find meaningful patterns when you look around is because you already have explanations. So finding patterns cannot be how you come up with explanations, or you get circularity. So to recap, you can't say what's similar or different without a goal or a problem situation or something to guide you. Like we saw with the photos. You need an idea of what matters, what to look for, what to pay attention to. Popper brought this up in a lecture once. He said to the audience, observe, and then he just waited. And people, after a bit, were like, observe what? They didn't know what to look at because there were so many different choices in the room. They didn't know what Popper meant, what he thought was important. So data doesn't speak for itself. You need ideas to interpret it and guide you. So one of the key problems with induction is when it says things like find patterns, it doesn't say which ones to find. When it says find similarities, compare how similar things are, it doesn't say which types of similarities to look for. So it ignores the multiplicity, the plurality of many different patterns, many different ways of comparing things. It forgets about all that and relies on your intuition. But you can't base a theory of how we learn and think and stuff based on assuming we already have intelligence and intuition and common sense. You have to explain those things in the first place. So I will talk more about induction in the next part. Subscribe if you're interested.